In this video, we're going to do a diagonalization example. So let's let A be this 2 by 2 matrix, and I want to diagonalize A if possible. So what that means is I need to find an invertible matrix P and a diagonal matrix D such that A equals P times D times P inverse. So recall that from the previous video, if I have a 2 by 2 matrix, what I'll need for it to be diagonalizable is because it's 2 by 2, two linearly independent eigenvectors. And if I have that, it's going to be diagonalizable. Okay, so let's talk about how we would solve this. Okay, so first I need to find my eigenvalues. And we get lucky here because our matrix A is upper triangular. So A is upper triangular, so we can see what the eigenvalues are right away. The eigenvalues are just the diagonal entries. They are lambda, so lambda equals -2 and 4. Those are the eigenvalues. So now let's find the eigenvectors for each of these eigenvalues. So for lambda equals -2, so the way I find the eigenvectors is I look at A minus lambda I, in this case A minus -2i. So that would be A plus 2i. So if I do A plus 2i, that would add 2 to each of my diagonal entries. So I would get 0 and then 6. And then the other entries stay the same, so I'd still have 3 and 0. Okay, and then what I need to do is I need to find the null space of this. So we're trying to find the null space of this matrix. Find the null space. So we have to, let's row reduce this. I notice that the second row is a multiple of the first, so I can zero out the second row. If I do -2 times row 1 and I add that to row 2 and insert into row 2, the first row stays the same, but the second row now becomes all zeros. And at this point, I could row reduce this further if I wanted to, but the equation is simple enough where I'm just going to write it out now. This first row gives me 3x2 equals 0. The second row gives me 0 equals 0, so there's no real point in writing that out because that's not helpful to us. So let's go ahead and write down what our vector x is. So x is two entries, x1 and x2, because there's two variables here. And x1 is free because there was no pivot in that first column, so we leave it as it is. And x2, well, x2 now we know has to be 0. If 3x2 equals 0, that means x2 better be 0. And then factoring out the free variable, we get x1. Okay, so I'll just let v1 be the vector 1, 0. But if I wanted to pick some multiple of 1, 0, which can be helpful if I have something with fractions, I could, as long as I don't pick just the 0 vector, because the 0 vector is not allowed to be an eigenvector. Okay, so for our other eigenvalues, we had lambda equals 4. So I now have to look at A minus 4i, which means I subtract 4 from each of the diagonal entries. So that's going to give me -6 and 0 on the diagonals. And the other entries are going to be 3 and 0. So this is also pretty simple, so if I wanted to write down the equation now, I could. But let me just show you guys what this would look like if I decided to row reduce this to reduced form. If I decided to row reduce this, I could divide the top row by -6. So that's easy enough. I'm just going to do it. I'll get 1 and then -1/2, and the second row stays the same, 0, 0. And that's in reduced echelon form now. And the equation that I get from this first row is that x1 minus 1/2 x2 equals 0. And now if I isolate for the pivot variable, I get x1 equals 1/2 x2. Alright, so now I can write down my answer as a vector, x equals x1, x2. And I know that what x1 is. x1 is 1/2 x2. x2 is free, so we leave that how it is. And factoring out the free variable, we get x2 factored out times the vector 1/2 and 1. Okay, so I'm going to let v2 just be the vector 1/2, 1. But remember that I can pick any multiple of this as long as I don't pick the 0 vector. So in particular, it actually might be nicer to pick 2 times this vector, because if I multiply by 2, I get rid of the fractions. So if I wanted to pick 1, 2 as an eigenvector that corresponded with this eigenvalue 4, I definitely could. Nothing wrong with that. It's a perfectly legitimate eigenvector for 4. Okay, so at this point I have found my eigenvalues. I found the eigenvectors. So there's 2 ways to see why our eigenvectors are linearly independent. So one is, if I look at the 2 eigenvectors, so one of them is 1, 2, 1, and if I flip back to the previous page, the other eigenvector was 1, 0. And these are not multiples. And if we have 2 vectors and they're not multiples, they're definitely linearly independent. So that's one way I could see that this is going to work. So at this point, I know that these 2 vectors my eigenvectors are linearly independent. The other way I can see that they're linearly independent is, we had a theorem back in section 5.1 that said that if our eigenvalues are distinct, and in this case they were, their corresponding eigenvectors are linearly independent. So we have those 2 ways to see that these eigenvectors are linearly independent. Okay, so it is diagonalizable at this point. So v1, v2 are linearly independent, and there are n of them. There are 2 of them. So our matrix A is diagonalizable, and that was part of what this question was asking. It is diagonalizable. So if it is diagonalizable, it said, well, then diagonalize it. Then tell me what D is and what P is. So D is a diagonal matrix where I put the eigenvalues as the diagonal entries. So one of the eigenvalues was -2, and one of them is 4. It turns out it doesn't really matter which order I put them in, as long as I make sure then the columns of P correspond. So let's say I put it in this order. So it's a diagonal, so the other entries are 0. So now when I write the matrix P has the eigenvectors as the columns. So I have to make sure, because I put -2 as the first entry in D, that I put the eigenvector for -2 as the first column. And that was, I believe it was 1, 0. 1, 0, yeah, I think that was right. And then for the second column, I put the eigenvector corresponding to this second eigenvalue here, to 4. And that was, we had decided to pick 1/2, 1. But if I wanted to pick the vector 1, 2, because that was nicer and I don't like fractions, I definitely could here. Okay. So we got to make sure that the columns of D and P correspond. So if I wanted to change the order that the -2 and the 4 in, I can, as long as I make sure then that the columns of P match up and they're corresponding. Okay, so in practice, when we have a diagonalization problem, when our matrix is diagonalizable like this was, we usually stop here once we get what D is and we get what P is. We usually don't write out what P inverse is. But let's say we wanted to check that this works. So if I wanted to check that A equals P times D times P inverse, we've seen before that this is equivalent to writing A times P equals P times D if I multiply the right-hand sides by P. So let's just check that it works. In actual problems, typically we'll skip this check and we'll stop where we are. But let's just check, because it's the first time we're doing this. So A times P, if we do that, A was -2 times 3, sorry, no, just 3, not times 3, 0, 4. And then P is 1, 1/2, 0, 1. That's what AP is. And then we'll also do what PD is. So P is 1, 1/2, 0, 1. And then D is our diagonal matrix, -2, 0, 0, 4. Okay, so if we multiply these out, if I multiply A times P, it turns out what I get. I'm just going to tell you, because at this point I know we're good at multiplying matrices. We'll get -2, 2, 0, 4. And if you multiply P times D, you actually get the same thing. -2, 2, 0, 4. And the fact that these are the same tells me that, oh, this works. This diagonalization is correct. So in practice, like I said before, Usually in a diagonalization problem, we would stop here. We would say what D and P are, and then we'd stop. We usually wouldn't do this check, but this check is how we could see that, oh yeah, I didn't make a mistake. It's one of the ways that we could quickly spot an error.